what's up, YouTube? I think that we are live. Let's make sure about that. Yes! Yo, what's up, Recuerdos de la Alhambra? It's good to see you, man. Today is the 23rd of January, 2026. I just wrote that in the wrong color, but let's go, dude. Good to see you. Let's practice some mathematics today. Why is this not working? There we go. Okay, one more time. 123.26. Here we go. I'm just going to be practicing some linear algebra. We'll be working some problems that I already did a couple of days ago, but I'm just going to work them again. What's up, man? Let me know if you're still here. So, a couple of days ago, I went through and I've started showing the method that I like to use to review old subjects that I used to know. Someone I used to know. I'm taking the first problem from every section, solving that, then taking the first problem from the second section, then the first problem from the third. So I solved the first problem from every section until I got to a problem that I did not know, and I had to actually read the section and learn how to solve that problem. And then now we're going to loop. Now that I got stuck on one and I had to actually read the section and learn this material or refresh my mind on this material, now we're going to go back and now we will restart from the beginning and let's level up and go with problem 1.1.2 from Frale. I just got this book back from my parents' house because I was visiting my parents for the holidays a couple weeks ago, and this is my favorite intro to linear algebra book so far. Out of the ones that I've seen, I have some other more difficult books, like Shilov is one that I've done a bunch of problems from in the past, and then I think up there is Strang. I don't like how informal Strang is. Shilov was just too advanced. It was very theoretical. It was very for mathematicians. It was difficult. It was really difficult, which was nice. I mean, and I could solve those problems. It tickled my brain in some ways, but it's not what I was looking for. I wanted this book. This book is just a really nice balance of rigor, like actual real mathematical rigor, but also for an introductory book. Hey, what's up, KS7 Edit? What's up, man? How's it going? Welcome to my mathematics practice stream. So I'm going to take the second problem from every section, solve it until we get to a section where I don't know how to solve it. Then I'll read the section, learn that material, and then we'll be done for the day. So this time I'm going to actually just write out the problems as we go instead of prepare all of them. So there's going to be a little bit more downtime for just chatting and stuff. So this problem is asking first, what is v plus w? Then what is v minus w? And then it wants us to sketch them in a coordinate axis. So if you add vectors, you add component-wise. So 1 minus 2 is -1. 3 plus 5 is 8, right? So even before I get started with that, we could just we could sketch v and w first. So v is 1, 3. So here is v. This is going to look prettier, I think, if we use a different color just for funsies. Why don't we use red? Here is v. V is red. W is purple. W is -2, 5. -1, 2, 5. -2, 5. Here's W. right? KS7 Edits, what's up? Are you a math person? Are you a fellow nerd like us? Recuerdos, are you still there, dude? It's good to see you. Y'all. People are just dropping like flies. Oh well. I don't know if a mathematics practice stream is the kind of content that YouTube wants. I would understand. If not, I would completely understand. But you know what? It's the kind of content I want to make, that's for sure. V plus W, let's put it in white. V plus W is -1, 8. So 1, 2, 3, 4, 5, 6, 7. It's going to be right about here. Right about there. -1, 8. White is kind of an atrocity right there, but hey, it's a different color. That's V plus W, and then finally V minus W. What is V minus W? 3, -2, right? And whatever, let's put that in this blue kind of color. V minus W. 3, -2. Right? So there is our beautiful little sketch. I'm pretty sure that that's correct. If not, I apologize. But I'm pretty sure that's right. Now, 1.2.2 from Frale. So, as I said, we're going to take the second problem from the second section. Let's see. It says V is 2, 1, -1. 2, 1, -1. The iPad is not going to be showing up very often. Okay, if I swap this and this, the iPad will show up better in the vertical stream. I don't know if we're going to get any vertical stream impressions. Because we're a tiny YouTube channel. Oh well. I don't know what I'm doing yet. We could do this. I could be right up top. I could be above and like really kind of try to optimize this. What are you practicing specifically? I am practicing some easy linear algebra problems. Linear algebra. Let me know if are you in the shorts feed? Are you seeing this vertically, or do you see the whole horizontal video? Because I'm trying to figure out how I want to present this this scene. We're doing linear algebra. Specifically, just introduction to vectors and matrices. This is fairly simple at the moment, but I'm reviewing linear algebra. So I'm going back to this old material that I used to know, and I'm coming back to it. Okay, you're watching horizontal, so I'm not going to stress out about like the center crop. What's your deal, dude? Are you a mathematician? Are you a engineer? Are you somebody who's learning math? Or, yeah, nice to meet you. Have you ever seen a math practice stream? I've never seen that before, but I like the idea. I love the idea of it. I just don't know if that's going to resonate with anybody. But it would resonate with me. I would watch a math practice stream. Okay, so that's the magnitude of V. The norm of V, I should say. 1.3. 1.3.2. Frale 1.3.2. So I'm taking the second problem from every section. Ah, you're a 12th grader. Cool, man. In the US or yeah, where are you watching from? Frale 1.3.2 has B is this matrix with a bunch of numbers in it. I'm going to go ahead and skip ahead. It asks, what is 0b? Well, 0b is going to be 0. In this case, it's a 2 by 3 matrix. So if you multiply by a scalar, it multiplies every entry. Integration or differentiation, like which is my favorite? Is that what you're asking? I prefer, I don't know, integration, I guess. Oh, you're from India. Cool, man. Cool. Yeah, that's calculus. I prefer linear algebra. I'd say neither. Neither integration nor differentiation. That stuff invokes infinity, and I'm not completely convinced that infinity exists. The continuum, the continuum of all real numbers, I'm not sure if that makes any sense. I'm a computer scientist. We love linear algebra instead. So we got Frale. I think that this is how I used to show them. Frale 1.4.2. Pretty simple. Okay, so A is 2, 4, negative 2, 2, 4, negative 2, 4, 8, 3, and negative 1, negative 3, 0. Negative 1, negative 3, 0, right? Negative 1, negative 3, 0. So it's asking to do row reductions into row echelon form, and then do some more row operations to get to reduced row echelon form. If you don't know what that means, let me know. Well, you may or may not know what that means. I don't know. If you don't, try to follow along. You'll see what I'm talking about here. All right. 4, 8, 3. Negative 1, negative 3, 0. So, to get to row echelon form, mate, I saw your live completely random on my feed. I wish you all the best in your life and practice sessions. Well, thank you, bro. Thank you so much, dude. I appreciate that very much. Yeah, I'm a former mathematician and I'm an ex-Google engineer. And right now I am trying to build a couple of practice streams here on YouTube. I'm also a classical guitarist, and I think it'd be kind of cool to have some background music, dude. Do you want to hear some background music? Shoot. Okay, this thing is not working the way that I wanted. Oh, no. Ah, dang it. Okay. I realize a limitation of my OBS setup right now. Media, background music, fall 25. Let me set up some background music for us so that people can hear something. Well, thank you so much, KS7 Edits. I appreciate that very much. Are you planning on doing any kind of like mathy kind of studies? Do you want to become like an engineer, like, software engineer or anything like that? That's what I did. I worked at Google. Back in the day. Let's go fall 25 recital. Loop. Use hardware decoding. Close file when inactive. Oh, that's me. the classical guitar. Let's put that quiet in the background, and let's also put this below everything else. So that, there we go. Okay, you should be able to hear some background music now. Let me know if I should turn it up or down. I think I should turn it up a little bit. Let me know if I should change the audio levels. So this is my secondary channel. JC Practices is my guitar channel. All right, 2, 4, -2. I'm going to row reduce this. I'm going to swap the... I don't know. It doesn't matter. I'm going to move that third row to the first and then multiply it by -1. I can see that as one operation. At the same time, I'm also going to double the third row and add it to the first. So double the third plus the first will give us a 0 in that first entry. -6 plus 4, -2, and then -2, right? Double the third plus the first. Yeah, double the third plus the first. And now, I don't know, subtract 2 times the first from the second. 4 minus 4 is 0. 8 minus 8 is 0. And then 3 plus 4, right? 3 plus 4 is 7, right? And now this is indeed in row echelon form, not unique, right? So that is not unique, but reduced row echelon form is. So we can divide that third row by the scalar to get 0, 0, 1, and then clear out all the entries above. And then after doing that, we will then 0 out the second, and then clear out the entry above it. So the reduced, I'm kind of taking too many shortcuts probably for like this level of the book, but reduced row echelon. The reduced row echelon form is unique. And that's a useful thing to remember. Now we're going to go frale 1.3.2. Let's take the third section, second problem from the third section. Oh, wait, no, the second problem from the... Oh, wait, we're already going to the fifth. What am I talking about? I went the wrong way. We've already done a bunch. 1.5.2. Inverses of square matrices. This is good stuff. I could name the topics here. Inverses of square matrices. Right? Okay, so find the inverse if it exists, and then B, express as a product of elementary matrices. Right? So that's the challenge with the matrix being 3, 6, 3, 8. 3, 6, 3, 8. So we are looking for some matrix A inverse such that when you multiply them together, we get the identity matrix. This is kind of like, what is the inverse of 2? The inverse of 2 is, I'll even write it this way. What is the inverse of 2? We want some number such that when we multiply them together, we get the number 1. What is that number? Well, it's 1/2. What is the inverse, multiplicative inverse of a number? It's the fraction with the number in the denominator. That will cancel out 2 to be 1. It'll like, yeah. It's a multiplicative inverse. This is the same idea, but now with these objects, which are matrices. They're blocks of numbers with special different multiplication rules on them. So the way we can do that, one way we can find an inverse is with this one weird trick that works very nicely. We adjoin the inverse matrix. And because in this problem we want to express as a product of elementary matrices, I'm going to track every individual operation individually, separately. So I will keep the first row. I will preserve the first row, and I'll subtract the first row from the second. So 3 minus 3 is 0, 8 minus 6 is 2, 0 minus 1 is -1, and 1 minus 0 is 1, right? This might feel a little redundant, but it makes sense, trust me. 0, 1, -1, 1. This is the row operation this is the elementary operation that I did. I subtracted the first row from the second. Like this matrix E1 will always subtract the first row from the second. We can see that here, like as an example. 1, 0, -1, 1. If we apply that to any matrix A, B, C, D, how do we multiply matrices? We do the dot product of a row with a column. So the first row dot product with the first column is going to be A plus 0C, A. And then same thing with first row second column is going to be B. So it, as I said, keeps the first row the same. And now we'll see with the dot product of the second row with the first column, -1 times A plus C. Well, that's like C minus A, right? And then -B plus D, well, that's the same as D minus B. So that's what we just described. We subtract the first row from the second, C minus A and D minus B. So that operation can be represented with this matrix. And that's the operation that we performed here. Now we can keep our nice whole numbers for a moment. And we're going to subtract 3 copies of the, we're going to subtract 3 copies of the first row, or of the second row from the first to get a 0 in this entry. 6 minus 6. Then in the adjoined matrix, 1 minus 3 times negative 1 is going to be 3 plus 1, right? Yeah. And then 0 minus 3. I'm not stuck on like what the what the math answer is. I'm stuck on like how to explain out loud what I'm doing sometimes. What does the line in the middle mean? Good question. It doesn't really mean anything. It's just organizational. Great question. Thank you for asking. So we had the original matrix A. A is, in this case, 3, 6, 3, 8. 3, 6, 3, 8. I'm creating a new matrix that is A appending the inverse matrix, right? So the line is just organization, just to remind ourselves that we like appended or adjoined this identity matrix on the right hand side. So 3, oops. Good question. Thank you for asking that. 3, 6, 1, 0, 3, 8, 0, 1. You don't need the line, but my book shows the line just for the reminder of like, you know, it's kind of like we're solving like a left-hand side and right-hand side of it, but it's literally just organization, kind of style or something. It's kind of like we're squishing together like a dot append or something. Maybe if it were like code, something like that. We're like combining those two matrices, squishing them together. I hope that makes sense. Okay, so thanks. E2. What did we do in this again? We subtracted 3 copies of the second row from the first, and then we kept the second row the same. So here is the operation that I did here. I subtracted 3 copies of the second row from the first. Siddharth, math stream, let's go. Yeah, dude, what's up? We're practicing some linear algebra right now. I'm taking the first problem from the first section, and then the first problem from the second section, and then the first problem from the third section. Yesterday I got up to the 8th section, and then I got stuck on that problem. So then you loop, right? And now we're going to go 1.2.1, what am I doing? 1.1.2, 1.1.2, 1.2.2, 1.2.2, 1.3.2, and we'll see how far we can get. We do matrices. Yeah, we're doing some kind of elementary linear algebra right now. So we started, section 1 was vectors, adding vectors, drawing vectors in an axis. Section 2, computing a norm. Section 3, some matrix algebra, multiplying a matrix by a scalar. Section 4, row reductions, reducing a matrix to row echelon form, and then reduced row echelon form. I am just doing math for fun, KS. Thanks for asking, dude. Yeah, I just love math. I mean, it's kind of for fun. It would be a dream if I could start teaching math again, like as a private tutor. I teach math, but like kind of more K-12 high school math. I'd love to teach math like college level math to hobbyists. So I have a practice stream just like this for guitar. That's what we're listening to. And that's where Siddharth is from. What's up, Siddharth? Good to see you, dude. And it took a long time, but I've started building up a really cool community of hobbyists, of guitar hobbyists. I'd love to build a math hobbyists community too. So yeah, that's what's up with that. Okay, so yeah, we're gonna see how far we can get in this lap until I get stuck. So let's get back to this problem. Thanks for asking. I'll erase all this. I am a former mathematician or math major or something, and I never actually went to grad school, but I took lots of master's level courses. I would love to rebuild my love and passion for mathematics, and I think that YouTube can just be a great way to build deep hobbies like that. Technically speaking, this thing wants a series of elementary matrices, so this should be 2 steps, even though I want to just race right ahead and get there. So we're taking a third of the first row and nothing from the second, or, not modifying the second. And then the final step is take half of the second row. I should have said over here that the game right now is to go from A adjoin I, do a bunch of row operations, and then get to I adjoin A inverse. Like that. This is what we're doing. If you keep doing row operations until the left-hand side of this combined matrix is the identity matrix, then the right-hand side of that line is A inverse. So that's what we did. This is now in the form of A. Oh, wait, no. What am I doing? Identity A inverse. Cool. So we are almost done. E4 is 4, 3, -1. Oh wait, no. That's A inverse. What did we do in this last operation? We took half of the second row. 1, 0, 0, 1 half. Cool. So we are just about done. A inverse is 4/3 and -1, and -1/2 and 1/2. I want to show 2 things. 1, A times A inverse should be the identity matrix. So let's see if that worked. Hey, Fated FX01. Ayo, what's up, buddy? How's it going? Well, welcome to my practice stream. My name is John. I am a passionate math hobbyist, and I would love to build a practice stream here on YouTube, practicing mathematics as a hobbyist. 3638 times 4/3, -1, -1/2, 1/2, right? I want to verify that this should work, that this fact should work. Let's see. Dot product of a row with a column. So 3 times 4/3, 3 times 4/3 is 4. Yeah. We have 4 minus 3. I'm just trying to show everything very explicitly. 4 minus 3 is 1. Great. Now, oops, that didn't work the way I wanted it to. Oops. Dot product of the first row with the second row, right? -3 plus 3. -3 plus 3 is 0. Right? Cool. Dot product of the second row with the first of, well, whatever, with the second. -3 plus 4, -3 plus 4 is 1, right? So that one worked. And now, dot product of the second row with the first column is 4 minus 4. And that is indeed 0. So this fact worked out. You can work the same exercise yourself to see if you've internalized, how matrix multiplication works. You can show that multiplying them in the opposite order also is the identity matrix. And this is not trivial because in matrices, remember that commutativity is not always true. For any two matrices, AB is not the same as B times A. In the real numbers, it is true. You can swap your multiplications with regular numbers, but with matrices, you can't. You can't just always say that you can multiply in either order. Matrix multiplication is non-commutative, and that's a really important idea. But it is true always that A inverse, if a matrix has an identity, it's an identity on the left and on the right. So commutativity is true for invertible matrices with their inverse, but not for matrices in general. But just for a matrix practice, you can practice that one. So that's one thing I wanted to show. The other thing I wanted to show is the second part of the question. Express as a product of elementary matrices. Yoink. Let's grab all of these. Okay. I'm getting a little too fancy here, I think. But let's do it nonetheless. Okay, so I want to show it in the order of, like, first we did this operation, then we did that operation, then we did this operation, and then finally we did this operation, right? These were all of the elementary matrices, elementary operations that we used. So this is E4, E3, E2, E1. I'm going to duplicate those two. And now we're just going to multiply these last two. So again, dot products of rows and columns. 1 plus 3 is 4. 0 minus 3 is negative 3. 0 minus 1 is negative 1. 0 plus 1 is 1, right? Yoink. Now, multiplying these two. 1/3. Yo, no BS guide, bro. How's it going? Welcome to my math practice stream, dude. What's up, y'all? Probably offline for months. No worries, man. I have not tried any math questions from the JEE. I'd love to sometime, but I don't think I'm sharp enough right now to be able to solve those types of problems these days. I've been doing baby math. For a while. I'm just trying to rebuild the habit and the consistency, just get back into it. And I think that YouTube can be a great way to build a good positive habit, like especially for a practice stream. Okay, so multiplying those two, we have 1/3 times 4 plus 0. We have negative 1 plus 0. We have 0 minus 1, and we have 0 plus 1, right? And then finally, we have 4/3 plus 0. We have negative 1 plus 1. And we have 0 minus a half. And we have 0 plus a half. And hey, look at that. This is indeed the matrix that we found earlier. Neat. Ooh, your JEE was yesterday, Siddharth? No kidding. How did it go, dude? How'd it go? Congrats. I hope you can take a breather today, man. I know that those exams are crazy. How'd it go, dude? So we got 1 point Frale 162 next. Ooh, awful. I'm sorry, man. Sorry to hear. Section 6 is from chapter 1 is about homogeneous systems, subspaces, and bases. Cool. I don't think I'll get stuck on the second problem, but dude, there's some parts of this section that I might have to reread soon. And again, my approach here is I'm strict. I'm just going right to the problems, and I'm trying not to read the section at all unless I need to. That's going to tell me like where are my gaps through these problems. And at some point, we're going to hit a section where I just definitely don't know the topic at all because maybe I never learned it. Like section 8 was optional and my class never did it. Okay, so let's see. Frale 162. Determine whether the indicated subset is a subspace of the given Euclidean space Rn. Okay, so we are determining if this subset x comma x1, the set of vectors of this form, is a subspace of R2. Which book are you solving now? I am solving Frale. Frale and Beauregard. What's up, Time Pass? How are you? This is my favorite intro to linear algebra book. I haven't found any others that I liked as much. I'm not gonna lie, y'all, I did not like string. I just did not like string at all. This one is super nice. This one is great. I got it from my parents when I visited for the holidays. And this is the one that my class taught from when I took linear algebra. So I think it's nice. It's an intro to linear book, but it's definitely written with like mathematician style rigor and like clarity in the writing. It's definitely written by mathematicians. I mean, so was String. String is a mathematician, but like I get the feeling that it was written for mathematicians. Like a little more, whereas String kind of feels a little more written for engineers or something to me, but no. All right, let's see. If a subspace is, or if a subset is a subspace, it needs to satisfy two criteria. V plus W for any two vectors needs to also be in the subset. We need closure under addition. Ooh, math. Yeah, what's up, Blake? Good to see you, man. So we've got closure under addition. We need to have closure under addition, and we need to have closure under multiplication. Right? So we want to check these two properties. Let's yoink all of this. Whoa! Try doing that on a chalkboard, y'all. Try doing that on a chalkboard. Okay, so I need to take any two arbitrary vectors of this form, a and a plus 1. So this is a set of vectors where the second value is one more than the first value, right? And if you add two of them, is the new vector still of that form? No, it's not going to be. Adding the first components together, a plus b. Adding the second components together, we have a plus b plus 2, right? Not plus 1, right? So that shows that we don't even have to check this one. I mean, it also fails that one, but we don't need to necessarily do that work. We can see that k times a vector of that form is actually ka and then ka plus k. So this isn't this fails unless k equals 1. If k was 1, then yes, that still works, but bro, how's learning Asturias going? Dude, yeah. K7 edits. I forgot. So you're watching my guitar channel? Good to see you, Blake. Blake, how did you know about this? Are you all in the Discord? Are you all in the Discord and that's how you found this? Or have you subscribed to my channel in the past? Or what? Yeah, I wanna build this math channel. Does it sound like an interesting idea to you all like a math practice channel. Asturias is going well, dude. For a dono, I would play it right now if anybody wants to. I don't even have memberships or monetization at all on this channel, so I don't know how I do that. But yeah, Asturias is going well, dude. Chillin'. I will stream some classical guitar practice right after this. So if you want to see how Asturias is, I'll probably be practicing classical guitar in like 20 minutes, I think. 20. Asturias is good. Yeah, I think I'll definitely have it ready for my April concert that's coming up. So we got Frale 172. This is an optional section that's about application to population. So this is an optional section from the book. And he calls it population distribution, but it's really Markov chains. This section is really learning about what a Markov chain is. And we don't have to get into all the details about it this time, but population distribution can be represented by Markov chains really well. Oh, no way, you searched up my Insta and you found my series there. No way, let's go, dude. Hell yeah. The master plan is in the works, y'all. Somebody found my math channel and then found my guitar channel. I want like a nice little synergy of people, crossing over. Because I think classical music and math has some like serious overlap, dude. For real. Bro, you should absolutely follow my guitar channel, dude. I have YouTube. That's what I primarily do here on YouTube is practicing Asturias, practicing classical guitar. So definitely follow. You'll see it. You'll see me practicing it sometime. 12 a.m. here. Woo! Good for you, man. Okay, so let me see. I was catching up. JEE. It went awful. Not going to clear it this time probably, but I guess I'll try for the April attempt. Good luck, man. Good luck. What kind of math, what kind of problems stumped you, Siddharth? Can you tell us about any of the ones that were challenging? Okay, we got Frale 172. The matrix in question is 0, 1/4, 1 3/4. And the questions are, is it a transition matrix? And then, if so, is it regular? When I was doing these a few days ago, I had to look this one up, honestly. So I had to I did have to pause and do a lap on these. I'm not live solving these problems this time, but next time it will be live solving. Like I am live solving these again, but I've seen these problems before. Next time we'll actually be solving problems that I haven't seen in the past. Let's see. Yeah, this one is a transition matrix, yes, because the columns sum to 1 and are non-negative. I think that the numbers all have to be non-negative. I want to double check about that, but I'm pretty sure that that's necessary too. So every entry needs to be non-negative. Yeah, I'm 100% sure. That's a requirement. We can think of these as like probabilities, like a 0% probability of the first entry and a 1% probability of the second state, and then 1/4 and 3/4. And we'll learn more about how to draw a Markov chain and things like that. This is a 2-state Markov chain. And if you're in the first state, I think the way it works is that there's a 100% chance that you'll move to the second state. But if you're in the second state, there's a 1/4 chance that you'll move to the first and a 3/4 chance that you'll stay in the second. So just thinking about that in that, from that perspective, it really seems like eventually at some point you're going to get stuck in the second node if this is a graph. Since we're doing matrices and determinants, let's talk about that. Ooh, okay. Yes, please stump JC Practices. I will think about that, and let's give it a shot in a moment here. All right, so it is a transition matrix. Is it regular? A transition matrix is regular if there exists an integer m such that a to the m this is pretty sloppy, but if there exists a positive integer m such that when you raise the matrix to that positive, to some positive number, it has no 0 entries, right? So a to the 1, m has to be bigger than 1 because a to the 1 has a 0, right? But what about m equals 2? I don't think that there's a very smart, we don't have like the mathematical tools right now, at least I don't know any, to be able to give like a theoretical argument that there must exist an m. I think that the only approach that we have right now is like, can we guess and check m? I think that that's, I mean, for now, this is my strategy, and I'm going to hope that maybe m equals 2 or m equals 3. I'm going to hope that one of these satisfies this, this condition. So, what is a squared? A squared is 0 1/4, 1 3/4 squared. Okay, and now I'm going to do this matrix multiplication in the perspective of the first row means 0 copies of the first row and 1/4 of the second. We replace the first row with 1/4 of the second row. Like, I'm going to think of these as like operating on rows instead of like dot products. Both ways work. So 1/4 of the second row is 3/16, right? And then the second row means row 1 plus 3/4 of row 2. So row 1 plus 3/4 of row 2 would have 3/4 in the first entry, and then 1/4 plus 9/16. 1/4 plus 9/16 is going to be 4/16 plus 9/16. 4 plus 9 is 13, 13/16, right? And voila. Yes. M equals 2 works, has no 0 entries, no zeros. Heck yeah. So yes, it is a transition matrix and it is regular as well. That is a concept I did not know. because my class did not teach Markov chains, did not get too far into Markov chains. All right, cool. Today, this one is a truly new problem for me. Let's do the first live solving from Frale. Let's go. Frale 182. This is application to binary. Hey, little gamer, OpenJE advanced previous year paper. I would like to try to solve some of those problems sometime. I've never looked at them. I've heard that they're hard. I would like to practice some JEE math sometime. Siddharth, are you still there? Now could be a time that I could try to think about the problem that you're talking about. Determinant problem. Let's see. Determinant problem was how long? I was given b I minus a equals I plus a, where I was given a matrix. I had to find the sum of diagonal elements of B transpose. A and B are 3 by 3 matrices. Were you given specific? I is the identity matrix. I assumed that. Yeah, I assumed so. But were you given specific matrices and you're trying to compute this, or is this for an arbitrary matrix, A and B? Are you saying A and B are arbitrary 3 by 3 matrices? And I'm not clear on like what the question is asking that you're referring to. And it's a determinant problem? Are you saying that the parentheses is a determinant? I've seen determinant as bars like that. Are you computing a specific matrix was given? Okay. And you're finding, you had to find the sum of diagonal elements of, so yeah, what you're being asked to find is the trace of a matrix is the sum of diagonals. The trace of a matrix is a super useful, powerful tool, fact about matrices. It's used a lot. I mean, so a useful fact here is that the diagonal elements of when you take the transpose, the diagonal, I mean, at least of a square matrix, the diagonal elements are going to be fixed, right? Those are going to be the same. So then the trace of a transpose equals the trace of the original matrix. Of B transpose. The trace of B transpose. I don't know if we have any algebraic facts about the trace. Can we say that that's like the trace of A times the trace of, or a trace of B times a trace of B transpose? I don't know. I don't think so. I don't know enough, man. I do not know that right now. Okay, B equals I minus A inverse X, I plus A. I minus A inverse times I plus A. Oh, this is crazy. Okay, and then Wow. All right. So you're saying that you had to find the trace of B transpose. Dang, dude. Okay. Well, I mean, huh. I don't know, man. Return of the King. What's up, Leo? How's it going? Dude, yeah, I want to rebuild this freaking stream, man. It's so niche, and it's hard to build the momentum when I've got another channel that's doing well, but I think I've started to find just enough people. Like Siddharth here. Siddharth here is a math person. So Siddharth meet Leo. Leo meets Siddharth. Leo's like a legit, proper, actual mathematician. And not a shitty, rusty hobbyist like me. Siddharth just took the JEE and he had this problem that he solved, but JC Praxis stumped. Officially stumped. Nice job. Might start doing more computer science videos soon. Really? Cool, dude. Cool. That's awesome. Yeah, I'm hopeful about starting to do these math streams again. I just want to build more math hobby habits, and we'll build up there. I'll be able to solve these JEE problems someday. But for now, oh, dude, Leo, you saw how bad Strang was. Try to follow Siddharth's, and Siddharth, stump Leo. Leo's legit. Like, it's easy to stump me, man, but try to stump Leo. You saw, I think that you saw a while back, maybe it was either you, Leo, or it was, why am I blanking right now? Oh my god, the other guy's name. You were that one other regular, I can't believe I'm forgetting his name right now, but Strang was terrible. I just did not like Strang. It was so poorly written, in my opinion. I'm sorry if he sees this video, but it was just like very non-rigorous. But pre-rigorous doesn't mean sloppy either. Like, this book is pre-rigorous also, but it's like way more clear. It's way more like pre-rigorous as in like, let's get you to math classes. Like, let's get you reading like real math books. Like, there are little historical notes, blurbs and things, but it is still written with like a lot of like definition, example, theorem, proofs are included. It's so much more written for like pre-rigorous math majors, if you know what I mean. Like, yeah, so I've heard that from people too, that people have not liked his book, but they like his lectures. I haven't watched any of the lectures. I'm a little too far into linear algebra that I don't want to watch videos. I'm trying to do linear algebra right now, like relearn linear algebra by just going straight to problems and not read the section if I can avoid it. So this one is the first live solving of one of these Frale problems for now. Application of binary linear codes. Let's do this. Binary linear codes. So this is super cool. I've known that this is a application of linear algebra that I never learned. My class didn't teach this section. We skipped this optional section. But in some of my computer science classes, we did learn about the idea of Huffman codes. These are Huffman error correcting codes. And yesterday we solved the first problem. Let the binary numbers 1 through 15 stand for those letters. I'm going to copy all this. I'm gonna, what am I gonna do? Let's copy this. Remind ourselves of this problem down here. This was problem 1, because now this one says it's unfortunately not just like another problem. Good. It says with the same understanding, same as 181, use nearest neighbor. This is cool. I think I'll be able to do this. Use nearest neighbor decoding. Yeah, so this is kind of like, do you understand the definition of the Hamming distance of 2 binary vectors? Use nearest neighbor decoding to decode this received. I'll be able to do this one. To decode this received message. So the idea of Huffman error correcting codes is that you've got this like dictionary where you take like a 4-bit message, convert it to a 7-bit message, like the letter A being 0001, we replace that with 0001011. So for each of these, well, maybe not all of them, but yeah, all of these are replaced with some other code in a way that adding that extra information can resolve problems. Like if one of these bits were flipped, if like this 0, like a sun flare or something changed, or like there was an error writing to a SD card or something, and that 1 bit was accidentally written as a 1 for whatever reason, we could still, well, I got this backwards. If one of these was flipped, then we could still understand that what was intended was 0001. Does that make sense? I don't know. I'm trying to give a brief explanation for people who've never heard of this idea. Let's do this. So we're going to decode this message. Have to head out to lunch now, but wish you luck. Hey, thanks, man. Thanks for stopping by, dude. Yeah. Not really trying to stump anyone, but it's fun to exchange math problems. Yes, that's what I mean. I just mean some people out here do want to solve math problems for fun and stump each other. I don't mean to put anybody on the spot. But yeah, I really like I like this book. Frale is really nice. Try the class 12 insert textbook. Nah, I don't know what that is. Haven't heard of it. All right, we've got nearest neighbor decoding to decode this. 0111001. 1111111. 010110. And then a bunch of zeros. 1, 2, 3, 4, 5, 6, 7. I did that right. 1100, 1100, 110. Got a bunch of ones. 1101, 1101, 000. And then finally 110, 1110. Cool. I think I need to move all of this further down. Okay, I'm not going to copy the whole table over because it's not that interesting. But there's a table, and I will definitely just I don't know, copy things over. So this looks, this one, these for sure I remember are preserved. So those are the original messages, those are not, those were not corrupted. There's no flipped bits. Those are in the Hamming 7.4 code. So I will write those. The corresponding inputs are these. 2, 3. Okay? So those are done. Those are easy to check. Now 0, I'll look for any others that are in the table. 0, 1, 1, 1, 0, 0, 1. This one is, why am I using a different color? We'll just go straight to, all of the yellow ones are uncorrupted. 0, 1, 1, 1, 0, 0, 1. 0, 1, 1, 1, 0, 0, 1 is the same as 0, 1, 1, 1. 1, 0, 1, 0, 1. 1, 0, 1, 0, 1, 0, 0. I don't see that one. Maybe I'm blanking, but let's check the next one. 0, 1, 0, 1. 1, 1, 0. Yeah, 0, 1, 0, 1, 1, 1, 0. This one is uncorrupted. 0, 1, 0, 1, 1, 1, 0 is 0, 1, 0, 1. I don't understand how they were picked. There might, I mean, I noticed that the prefix of these are the same, but it's not always, like not all of them just match the prefix. But it does seem like that is intentional. Like the prefix of the Hamming code is 0101 in this case. 1101. 1101 000. 1101 1101 000. This one is also uncorrupted. 1101 000 is 1101. 1101. And 1100 1100 110 1100 110. This one is not. Cool. 1101 1101. These are not in the table. So the game right now is to figure out which of those, which code does exist that's the closest to these, right? 101 0. So what we do, I don't know what the notation is, the correct notation for this is, but we want to compute the Hamming distance. What notation do they use for this? Doesn't matter. I want to compute the Hamming distance of the code 1010100 with others. What's the best way to do this? I mean, I think just by inspection is going to be the best way. I see that there's 101. There's one that's close to it. 101. 1010001. This one exists, and it's pretty close. But it has 2 bits that are flipped, right? 1010. This one is different from this one, and this one is different from this one, right? So the Hamming distance is 2. What are the other possible ones? Is there anything better than 2? 101. Should I just write all of them just to, like, be super thorough? I mean, that's, I guess, what a computer would do. 1010001 1010001 1011010 1011010 11000 11000 11 1101 1101 000. Because my guess is that there's probably one of these that is going to be like a Hamming distance of 1. If there is, and I'm just not seeing it like immediately. Is there? Oh, okay. Yes, I spotted it. Yeah, with this method, I was thinking, okay, can I take a look at that suffix? Are there any that have this suffix in the table? That was I mean, it's kind of a hack, but I mean, I don't know. We're solving these problems from a book on paper, so it can't be that hard. Like, it's not going to be, like, it's meant to be something that you can spot with your eyes. And it is this next one that I was about to write. So either way would have found it. 1110100. That suffix is the same as this suffix right here. And then the only difference is the second bit here is a 1, whereas the second bit here is a 0, right? So for sure, this 10100 whatever, that thing should have been this, like the correct message that was sent, but then corrupted, was that one. And that corresponds to 11101 1110. 1110 right there. over here I wrote them in red, so why don't we do them in red as well? 1, 1, 1, 0. Cool. This is somewhat tedious, but very illustrative. So 1, 1, 0. Yeah. Just by inspection, now I'm spotting that the other one, 1, 1, 0, 1. Wait, 1, 1, 0. Shoot, it's not that one. Okay, 1, 1. Neat. I don't feel like writing all of these out. If I were doing this actually as a homework set, I would just write these in the freaking book on paper. I don't want to rewrite all of this because it's just kind of tedious. Because there's a lot of zeros and ones to check on. The idea here is 1, 1, 0, 0, 1, 1, 0. 1, 1, 0, 0, 1, 1, 0. We're computing the Hamming distance of that with all of the various vectors. And then the last one is 1, 1, 0, 1, 1, 1, 0. 1, 1, 0, 1, 1, 1, 0. With all these other vectors. If there's any that just have a Hamming distance of 1, then I'm confident that we're done. So now let's do like this one's close, right? It has the same 4-letter prefix, but the suffix is a Hamming distance of 2. So it's close, but that's probably not the right one. Then if I write, all the other ones are more. It's not that close. 1, 0, 1, 0. I see. Okay, thinking from the perspective of like, oh no, yeah, this is it. It's right here. So 1, 0, 1, 0. I was thinking of like, okay, let's take a 4-letter prefix and try to guess. Can we find anything with a 4-letter prefix? Nope. That is also, what am I talking about? That is also a Hamming distance of 2. There's 2 bits that are different. This one and this 0. So I don't think it's going to be that one. That's the only one that has that prefix. Aha! I found it. It's, I think, the next one. Oh, no, it's right here. I already wrote it here. Okay, so in this case, let's use another color. Let's use cyan. What am I freaking doing? What am I... Okay, I'm confusing myself right now. Solving math problems on an iPad is so foreign to me. I've done chem problems on it because I would have had to take a print of it otherwise, but never with math. I mean, I never did until trying to build this YouTube stream. This is brand new to me, dude. This is brand new to me. But it's kind of cool. Like, it's actually kind of cool. I would not, you know, use it for like submitting problems, like a problem set and like filling out homework sets or something with an iPad. But for teaching purposes, dude, I think it's actually like quite cool. I can like zoom in, use, you know, copy paste. I can like use different colors really easily. I think it's cool for teaching. If I'm totally honest with you, but let me know, like, what do you think? Is it confusing? Is it kind of cool? Does it work? Okay, so these are some of the Hamming codes that I've written out. There's a bunch more in total, but 11101111111. Of course, that's not it. 10100001 10101000 1001 101 1001 101 1000 1000 110. Okay. Yo, it's this one that I just wrote. I think it's this one, right? Because it's got no, it's not that. F. It's this one. Yeah, there it is. Okay, so I spotted that looking at the suffix. I was like, okay, is the suffix the same? And it was the same up to there, but this spot is different, and this part is the same. So, there it is. Hamming distance of 1. That code was intended to be this one. Well, yeah, I don't need to write anything there. And in the dictionary, 10001 this corresponds to 1000. So, are you not entertained? Are you not entertained? Last one. This is super tedious, but hey, it's a cool exercise. It's cool to do these by hand once in your life, I think. All right, 110 1110. That's a very distinctive ending to me. 1110. Do I see that anywhere? 1110. I don't see that anywhere in the table. But what about the prefix? 1101. This is not scientific, but 1101. Neither of those have Hamming distance of 2. Let's take the middle. So I'm going to look at the middle and compare. Which ones have that? 0111. Aha, 0111. I'm going to get rid of some of this intermediate work. Move all this down. I know I could duplicate it, but who cares? Let's just keep moving. I gotta wrap this up. This is taking a little longer than I wanted today. 1 0 0 0 0 1 1 0 0 1 1 1 0 0 0 1 1 1 0 0 1. This is, oh no, that's not the one. Just like that. 0 1 1. This is so tedious. 0 0 1 0 0 1 0 1 1 1 0 1 0 1 1 1 0 1 0 1 1 1 0. And this is the one that I just spotted. One. Like, ugh, kill me. This is so tedious right now. 0 1 1 1. Right there. I spotted that. And now looking at the rest. Oh, hey, the suffix is the same. This one is the same. The only flipped bit is right here. This one has a Hamming distance of 1. So that's it. That's the one that we're looking for. 0 1 0 1 0 1 0 0 1 1 1 1 0. Of course, most is 0 1 0 1. Hell yeah. 0 1 0 1. And now we get the delightful joy of decoding this frickin' message. Y'all. Who cares? This is out of order. Doesn't matter. And going back to our table from before. That'll copy. No, I'm not gonna. Let's see. So the final step in this problem is going to be decoding using the alphabet. So space is 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1. I'm just going to write a few of these, or just enough to get started. A, B, C, D, E. How else can I think of this? Okay, this is the number 0. This is the number 15. This is the number 8, right? Yeah, that's the number 8. This is the number 5. This is the number also 5. Oops. And let's work some of these other ones. So this first number is 4. 0 1 1 1 is 4 plus 2 plus 1. That is 7. Right? This next one, 1 1 1 0, is 8 plus 4 plus 2, which is 14. And those are, oh wait, no, last one is here. This is 8 plus 4 plus 1. 8 plus 4 plus 1 is 13. Right there. Hooray, we're getting so close. The last step to decode this message is translate these numbers to the original letters. Yeah, this is all pretty new to me too. This is called Huffman encoding, or Huffman coding. This is Huffman 7.4 encoding. These are error correction codes. So it's kind of cool. It's like you send a binary message, and there can be a corruption in the data, but you can still guess what the original message was meant to be, even though there were like flipped bits, based on the fact that like how different, like there's like these valid, correct, expected code words, but if you get a code word that's different than one of the expected ones, then you look up which one is the closest, and you can still like recover the original data. So even though the message was corrupted, we can still decode it and figure out what the expected message was meant to be. So so that's the last step right now. We're decoding this message. So zeros, I know, are spaces. And I remember that 15s are the letter O. That's the last letter. And now I'm going to count with my fingers the other letters. A, B, C, D, E. E is the fifth letter. And I see two of those, here and here. E, F, G. G is the seventh letter. N, O. N is the 14th letter, right there. Gone. Gone space something. A, B, C, D, E, F, G, H. H is the 8th letter. And now the 13th. A, B, C, D, E, F, G, H, I, J, K, L, M. Yep, that's what I was guessing. All right. So the message is gone home. Voila, we did it. That was so tedious. But a computer can do this instantaneously. But a human, it takes a little while to do this. And especially if you're like recopying the stupid table. These are all of the code words. I mean, if I wasn't lazy and I had just wrote all of this first into the iPad, I'll show just a couple of them. Because the table itself, I don't know why, just morally I refuse to like just work directly from the PDF. I feel like that's like just a little too far in the copyright infringement, argument of fair use. I think that everything I'm doing here is very fair use. But yeah. Rewriting all this is like definitely tedious. What am I trying to illustrate right now? In the book, this is how the table shows. These are the code word. There are more, but we've got a message and we've got the code word. And then starting at the bottom, the message is 1111, but what you actually write down is 1111111, like seven of them. So right. So these are all, yeah. Like there's a whole table where these, like you just look up this dictionary, you look up this expected set of code words, but you received some message that's not in, you get something that's not in any of the expected ones, and you find which one is the closest message to one that, you know, that is expected. And then once you find, you know, whatever, maybe it's this one, then you look up, oh, that one corresponds to whatever this message, the like encoded message was, you could still guess that they intended to send that one. Yeah, this is very much related to semiconductors, and yeah, I mean, you use this binary all the time for circuits and semiconductors. I don't know enough. I hope to learn more. I know that you can really use a lot of linear algebra for solving circuits problems and stuff. Okay, so we did that, technically speaking, without needing to actually read the section. The stream is going way longer than I intended for it to. So I don't know if I want to do a lap through chapter 2, but we will eventually need. So I'm going to go a little bit more. Maybe guitar stream will be late tonight, not now. Frale 2.1.1. I want to be strict about this idea. Frale 2.1.1. Finally, let's keep moving on. This is independence and dimension. Give a geometric criterion for a set of two distinct non-zero vectors in R2 to be dependent. Geometric criterion. They lie on the same line, right? If two distinct non-zero vectors are dependent, then that if they're non-zero, then it has some sort of magnitude, non-zero magnitude, and then the other one, you know, is a scalar multiple of the first. Could be pointing in one direction or pointing in the other direction, but no matter what, they're lying on the same line in R2. Frale 2.2.1. Hey, it's late. Gonna go to sleep now. Take care, Sidar. Thanks for stopping by, man. I hope you enjoyed the stream. Let me know, dude. Let me know if you want me to do more of these. It's definitely a different kind of idea, right? Good to see you, dude. Thanks for stopping by. We've got 2.2.1. The rank of a matrix. Now, whoo. Oh goodness, I don't remember this as well, so we might get stuck on this one. I might have to look into the section for this one. Might have to actually look into the section. I think we got this. I know that the rank is going to be 2. It's rank 2 matrix. So I believe on the problem like this, 2, 0, negative 3, 1, 3, 4, 2, 2, we can row reduce because row reductions will preserve the column space, row space, null space, all of those things, I think. So double the second minus the first. Double the second minus the first would be double the second minus 3 times the first. That is. Double second minus 3 times. So 9 plus 4. Right? 3 times the first minus double the second. Could be another way of 3 times the first, 3 3 minus 4, negative 1. Did I get a sign backwards? Yeah, I did a sign change wrong. Okay. Woo! I'm confusing myself. I'm tired. I need some coffee or something. Double the second minus, so 6 minus 3. 6 minus 3 is 3. Cool. Now I know that, therefore, because we have 2 non-zero pivots, part A, rank is 2 based on that. A basis for the row space. I think that a basis for the row space would be the 2 row vectors. Basis for the column space, I believe, is going to be 2, 0, and 0, 8, which is equivalent to 1, 0, and 0, 1. If I understand correctly. Basis for the null space. Man, I don't remember this as well. So what is the null space? The null space of a matrix are all of the vectors v such that AV equals 0. So How does this go? How does this one go? I think we do something like... From this row-reduced matrix, 2, 0, -3, 1, 0, 8, 13, 3. We can view this as the set of equations like 2a minus 3c plus d. We want to solve this times a vector equals 0, 0. Right? So if there was a vector in the null space, it would be of the form a, b, c, d, like this. And we want to solve this equation. So that means 2a minus 3c plus d is 0, and 8b plus 13c plus 3d equals 0, right? So we can, c and d are free variables, right? We can take anything for c and d. I think what we do is we choose some special values. Since we can choose anything for them, we can take some special values. Like, what if CD were 0, 0? Or what if CD were 1, 0? And then we would solve for is this how we do it? Damn it, I am a year too early. Ah, dang, dude. Are you blocky? Are you going to take linear algebra next year? Or you can watch these videos then? Yeah, it's kind of a challenge about building a math stream. Like, most people are not studying exactly this topic. What kind of math are you doing these days? Okay, so CD were 0, 0, then we have 2a equals 0. Therefore, a equals 0. And 8b. Oh wait, I think, do they need to be non-zero? Yeah, this was my first intuition. My first guess was that they need to be non-zero numbers. This was my first guess. So if C was 0 and D was 1, then our set of equations are like 2a plus 1 equals 0, and 8b plus 3 equals 0, right? So then a equals -1/2 and b equals -3/8. So then the vector, one vector in the null space would be the vector -1/2, -3/8, 0, and 1. This could be a perfectly fine vector, or even better, we could multiply everything by 8. So if we multiplied everything by 8, we'd get this. Then we have nice positive integers. Well, nice integers, not positive, but if CD were 1, 0, then we solve 2a minus 3. I'll leap forward on this. So if d is 0, then 2a equals 3. A equals 3/2. Right? 2a minus 3 equals 0. And in the second equation, we have 8b plus 13 equals 0. So b is negative 13/8, right? So then our vector could be 3/2, negative 13/8, 1, 0. Or, better yet, multiply everything by 8 again, and then we have 4 times 3, negative 13, 8, 0. Yo, this one was like a little trickier for me, I think. Now, let's just confirm. So my claim is that the null space of this matrix is the span of -4, -3. I don't like negatives. Let's make that 4, 3, 0, -8. Pretty. Nice and pretty there. 12, -13, 8, and 0. Let's just verify one of these worked, that I didn't make like a typo somewhere. A times V equals 0. Did we get this right? A is 2, 0, -3, 1, 3, 4, 2, 2. And let's try it with 4, 3, 0, -8. So we have 8 minus 8. Yeah, 8 minus 8 is 0. And we have 12 plus 12 plus 0. What? Shoot. Minus 16. Did I fuck this up? Where did we go wrong? 4, 3, 0, -8. 3, 4, 2, 2. Well, those don't add up to 0. Multiplied everything by 8. Fuck something up. What happened? What happened? 2a plus 1 equals 0. 8b plus 3 equals 0. A is negative 1/2. B is negative 3/8. Yeah, I'm kind of tired now. Did I mess this up? Where did I go wrong? Did I get the row reductions wrong? That would be embarrassing. Double the second row, subtract the 2 times the first. 6 minus 4. Oh, wait. 6 minus triple the first. Yeah. Double the second minus triple the first. 6 minus 6. 8 minus 0. 2 plus 9. Shoot. Okay, there it is. That 13 should have been an 11. Ah, gosh, dang it. Okay. But I found the problem on my own. I did not have to go through the section. So I'm still going to call this a win if I can fix the problem, if we just rework this problem. And, oh gosh, okay. That's annoying. All right, so that's where it is. Let's just make sure that this last one was correct. Double, so 4 minus 3. Yeah, what was I doing? Okay. Double the second row minus triple the first. Right? Double the second minus triple the first. Yeah, so this should have been an 11, and this should have been a 1. An 11 and 1. The rank is still 2. We still got to the same rank. The basis for the row space then would be that, and this one is 11 and 1 now. Basis for the column space is still true. Basis for the null space. So now this one is an 11 and this one is a 1. C and 1D. Okay, I will attempt this one more time. Oops, don't paste an image, paste the whole thing. Okay, so what do we do here? We take 2 special cases. CD equals, let's go 1, 0, and then CD equals 0, 1. A equals 3 halves. B equals negative 11/8. CD equals 0, 1. A equals negative 1/2. B equals negative 1/8. Right? Then our vectors can be 3 halves, negative 11/8, 1, 0, or equivalently, because any scalar multiple will also be in the same span. So I want to multiply everything by 8. So we have 12, negative 11, 8, 0. And over here, negative 1/2, negative 1/8, 0, and 1. Multiply everything by 8. Negative 4, negative 1, 0, 8. Negative 4, negative 1, 0, 8 sounds very familiar. Negative 4, oh yeah, negative 4, negative 1, 0, 8. So we were testing a swap whether it was on the left or right of the iPad earlier, but it's all the same. So now we are going to test null space of A. My claim is that it's a span of these two vectors. 12, negative 11, 8, 0. I don't know if it matters to think of. It should be. They should be column vectors, shouldn't they? 12, negative 11, 8, 0, and negative 4, negative 1, 0, 8. Pretty sure that that's right, and right now I just want to verify with a couple of examples. So this whole thing is extremely similar. It's just that one of those numbers is different. Let's duplicate it one more time. Let's do these in order. 12, negative 11, 8, 0. And, okay, this is a little OCD right now, but 4, 1, 0, negative 8. This is the one that we're solving earlier, so let's do that one first, just to feel good about ourselves. 4, oh, so 8 minus 8 is 0. 12 plus 4 minus 16 is 0. Yes. There we go. 12 plus 4 is 16, minus 16 is 0. That one worked. On this one, we have 24 minus 24 is 0. Yep. 36 minus 44. 36 minus 44. This feels weird. Okay. Wait. 36 minus 44 plus 16. That doesn't look right. Shoot, did I mess this up again? 36 minus 44 plus 16. Did I write down the matrix wrong? Because No, the original matrix should be the same, always. 12, negative 11, 8, 0. Am I blinking? Oh my gosh, okay. Why would the second vector work but not the first? That seems odd. Did I get a sign error wrong or something? So C is 1. 3/2. A is 3/2. What the heck? Three times 12 is 36, minus 44, plus 16, plus 0. Do I just not remember this correctly? Two zero negative 3 1 3 4 2 2. I wrote it all down right. What the hell? AB plus 11 plus D. That's so strange that one of them would work, but not the other. What the? Okay. No. Now I'm sniped. Now I really want to understand what happened here. 24 minus 24, the first entry is 0. 36 minus 44 plus 16. Just to be clear, this is 0 minus 8. And I want it to be 0, 0. I'm incredibly stubborn right now. I'm very, very stubborn about this. Why? Because I'm pretty confident that I do remember this is how you solve this, do this type of problem. So it's like a calculation error somewhere, but like I know the concept. I got the concept right. I was able to live dust off those cobwebs and figure it out on the fly. Like, what is the concept here again that we're supposed to do? So let's make the numbers just easier for ourselves or something. I don't know. I'm gonna, because I'm struggling, I'm gonna triple the first to do row reductions, and I'm going to double the second. 4, 4. And now I'm going to subtract the first from the second. Wait, what? Oh my gosh. What am I doing? Okay, all Okay, here we go. Here we go. There's the error. You see, this is why you don't... you don't try to take shortcuts. Trying to show like, oh, I can do all this in my head. I can skip stuff. This is so boring for YouTube. This is not engaging content. Let's just skip steps. So it's 13 and 1. The first time around when I did this, I got something different. I got like 13 and 4. The second time I got 11 and 1, but no, this should be 13. I got the 13 correct, but this other one, I think I had a 1 or a 4, but it should be 13 and 1 here. Okay, so that's why it's very useful to do that last parity check kind of thing. That last, like, just let's make sure that we didn't make an error somewhere along the way kind of step. So, row space and column space are not that interesting. I'm not going to bother writing them, but null space now we are solving 2a minus 3c plus d equals 0, 8b plus 13c plus d equals 0 with cd equals 1, 0 and cd equals 0, 1. Then this vector, I wonder if there's a faster way to have done all this. A is 3/2. B is negative 13/8. C is 1, D is 0. In this case, A is negative 1/2. B is negative 1/8. C is 0, D is 1. So the null space of A is the span of multiply everything by 8. I still want to work with whole numbers, not fractions. 12, negative 13, 8, 0. Second vector, multiply by negative 8. We have positive 4, 1, 0, negative 8. So 4, 1, 0, negative 8. Still, 4, 1, 0, negative 8 still worked correctly. This other vector, 12, negative 8, this solution this problem we need to try one more time. 12, negative 13, 8, 0. This is what we're going to try. Okay, 2 times 12, 24, minus 24 is 0. So that first entry worked. Now, 36 minus 4 times 13, I'm going to pause on that, plus 16, right? Well, I'm feeling very lazy, so this is 36 plus 16 is 52, minus 4 times 13. Yes, 52 is 4 times 13. Yes, so this is 0. Hooray! All right, so the right process worked. I knew the right concept. I knew the process. It was just stupid calculation errors. Okay, so we got it, technically speaking, without reading the section. That took a while. That took quite a while, but we did it. I'm going to cross it off in pen in my book. And I want to keep going today. This is a bad idea. I did not intend to go this long until we get stuck. 2.3 Linear transformations of Euclidean spaces. 2.3.1 Linear transformations of Euclidean spaces. Is T of x1, x2, x3 equal x1 plus x2, x1 minus 3x2 a linear transformation of R3 into R2? Why or why not? Whew. I'm tired, so I think that this might be the one that stumps us. Linear transformations of Euclidean spaces. Is this transformation a linear transformation of R3 into R2? Why or why not? How do I know this? Okay. I'm wiped. I usually try to reserve the energy to read the section and freaking try to read the section and solve the problem, but right now I'm like super wiped because I've been going way longer than I had planned today and I haven't eaten. So, jeez. I'll skim the section and remember this real quick. Oh my goodness. Nobody's ever going to watch this. Okay, so here's the key. Definition. Yeah, I thought that it was going to be preservation of addition and scalar. I thought that it was like similar to closure, the closure properties. A function t from Rn into Rm is a linear transformation if it satisfies two conditions. 1. T of u plus v equals T of u plus T of v. 2. T of RU equals RT of U. Okay, great. This is what I need. I got stumped, but now we'll be able to do it, I think. So, T of A plus A1 plus B1, A2 plus B2, A3 plus B3 equals, by definition, the first component plus the second component, A1 plus B1 plus A2 plus B2, x minus 3x2. This looks like a linear transformation to me. It really does. I think that this is. Yeah. The first component minus 3 times the second component. Yeah. Yep. Cool. So it preserves addition, and now we need to check that it preserves multiplication. So the rule is that the first component is adding the two. Let's see. Let's not use a bunch of subscripts in this case. Because we don't have two different vectors, we just have one vector, AB. Isn't that it? Yeah. Okay. And yes, we see that we can factor out a k out of everything. Cool. Done. So it is. But this is the problem where I had to read a little bit of the section. I only had to like glance for a second at the definition. But it's mostly just because I'm white. Thanks for watching. This was a pleasure. This was a longer stream than I expected, but we did it. We did a whole lap through linear algebra sections until I got stumped. Thank you for watching, and if you enjoyed this, please hit the like and subscribe. Let me know. I'd like to do more math streams this year, so let me know if you want to see that. Thanks for watching.